Atomic spectroscopy is a branch of analytical chemistry that involves the study of the electromagnetic radiation absorbed or emitted by atoms. It is widely used for qualitative and quantitative analysis of elements in samples. Atomic spectroscopy techniques include atomic absorption spectroscopy, AAS, and atomic emission spectroscopy, AES, which provide information about the elemental composition and concentration of samples. Here's how to analyze atomic absorption and emission. Atomic absorption spectroscopy, AAS. A. Principle. AAS measures the absorption of electromagnetic radiation, usually in the UV visible range, by ground state atoms in a sample. When atoms absorb radiation at specific wavelengths corresponding to their characteristic electronic transitions, they undergo a transition to excited states. The intensity of the absorbed radiation is proportional to the concentration of the analyte element in the sample. B. Instrumentation. Light source. A continuum or line source emits radiation at specific wavelengths. Monochromator. Selects the desired wavelength of radiation. Sample compartment. Contains the sample solution or vaporized sample. Detector. Measures the intensity of transmitted radiation. C. Analysis procedure. Prepare the sample solution by dissolving or digesting the sample in an appropriate solvent. Aspirate the sample solution into the sample compartment of the AAS instrument. Pass the radiation emitted by the light source through the sample solution. Measure the intensity of transmitted radiation with the detector. Compare the absorbance of the sample to a calibration curve or standard solutions of known concentration to determine the concentration of the analyte element. Atomic emission spectroscopy, AES. A. Principle. AES measures the emission of electromagnetic radiation by excited atoms in a sample. When atoms are excited by thermal or electrical energy, they transition from lower energy levels to higher energy levels. As the atoms return to their ground state, they emit radiation at specific wavelengths corresponding to their characteristic electronic transitions. The intensity of the emitted radiation is proportional to the concentration of the analyte element in the sample. B. Instrumentation. Excitation source. Provides energy to excite atoms in the sample, e.g., flame, plasma, or arc. Optical system. Collects and disperses emitted radiation. Detector. Measures the intensity of emitted radiation. C. Analysis procedure. Prepare the sample by dissolving or digesting it in an appropriate solvent. Introduce the sample into the excitation source, where it is atomized and excited. Collect the emitted radiation using the optical system. Disperse the radiation using a monochromator to select the desired wavelengths. Measure the intensity of emitted radiation with the detector. Compare the intensity of emission lines to a calibration curve or standard solutions of known concentration to determine the concentration of the analyte element. By following these procedures, atomic absorption and emission spectroscopy can be used to analyze the elemental composition and concentration of samples, making them valuable tools in analytical chemistry for a wide range of applications, including environmental monitoring, pharmaceutical analysis, and materials characterization.